Exercise 1.1, question 4. Use Euclid's division lemma to show that the square of any positive integer that you might take in the world, take the square of that, it is either of the form 3m or 3m plus 1 for some integer m. Now, this Euclid's division lemma we discussed in detail in question number 1 of this exercise, but we have it stated here. This is exactly what this is. You have two integers a and b, then you can divide a by b. As a result, you're going to get the quotient q and the remainder r, and all four of these are always going to satisfy this relationship. Dividend will be divisor times quotient plus remainder, and the remainder will always be less than the divisor, greater than equal to 0. Well, this is about what the lemma is, but the question wants me to use this lemma to show something. Now, right now, it does not make much sense. It's like square of an integer, of a positive integer. How will it be of this form? Integers are 1, 2, 3, 4, 5. Squares would be 1, 4, 9, 16, 25, and so on. How does this m come into picture? Well, we have seen a similar question number 2 of this exercise, but that was one level below this one. And why is this particular question at a higher level? It's really because of this one word that you're taking the square of some integer. Question 2 itself did not have any square or any cube or anything. That talked about positive odd integers themselves being of a certain form. 3 different forms to be precise. Anyway, let's discuss this particular question here. So they've given us a hint also. They're saying let x be any positive integer, then it is of the form this, this or that. Now this might not seem very relatable. So for this, I am stressing on question number 2 again and again because the foundation is based on that question. Let me explain what this is. So you will just take one random integer, the one that you're talking about, whose square you will take later because you want the square of a positive integer, right? So this is what I'm calling x. So there's your statement. Let x be any positive integer. Now, according to the lemma, we have a, that is the dividend, and we have b, which is the divisor. Now, in place of a, my dividend right now is x. X will be my dividend, and b, which is the divisor, has to be this number that I see, 3m, 3m plus 1. So it's 3. It's a multiple of 3 in this case, or it's a multiple of 3 plus 1 in the second case. So this is what I take b to be. This is exactly what we did in question 2 again. So let x be positive integer and b be 3. Now that I have these two numbers, I have x and I have 3, I can use the Euclid's division lemma to write down this kind of a relationship. So what will happen is that there will be a quotient q, there will be a remainder r when I divide my x by 3 like this. So suppose the quotient I get is q, I don't really know the value, and the remainder that I get ultimately is r. Then according to this little relationship here, I can say x is equal to 3 for b, 3q plus r. Where what do you know about r? You know that this remainder r has to be less than the divisor b, which is 3 for me, and has to be greater than or equal to 0. So that really gives me 3 possible values of r, 0, 1 and 2, because I cannot have 3, it's less than that. For each of these now I will get a value of x. How? I will just keep putting the value of r from here. For example, if r is 0, I just put 0 here, and as a result my x will just be 3q. Second stage, I'll just put r equal to 1 in this place, and I will get x is equal to 3q plus 1. And as this final stage where r is equal to 2, I'll just put that 2 here, and I will get my x is equal to 3q plus 2. So this is what the hint was that the book was giving us, but we had to really understand how to get till here. Now finally we have gotten till this stage that any positive integer in the world can be expressed in one of these three forms: 3q, 3q plus 1, or 3q plus 2. But remember, my question is not just about any positive integer, it is about the square of any positive integer. So now that I know something about x, I have to square it. So I will continue the solution from here. Let me just clear up some space, spend time on this, and then go on for the rest of the solution. Alright, so here is the main part that we had till now from our solution. We have to talk about the square of any positive integer. This positive integer we called x, and now we know that this x can be one of these three, in one of these three forms. Now what I have to do is I have to square this because my idea was to have the square of this positive integer. So all you need to do is square each of them one by one. So you can pause the video and try squaring that because these are things you already know, and then resume to see if I do it the same way. Okay, I hope you tried. The first one, which is the square of 3q squared, will come out to be 9q squared. The second one, when you square this, this will be squared using the identity a plus b whole squared, which is a squared. So 3q squared plus b squared, so 1 squared, plus 2 times a times b, like this. Then you will just write each of these simplified. Let me just do that. There you go. And finally, if we square this last possible value of x, then again you will get a squared, 3q squared, which will be 9q squared. 2 squared is 4, and then 2 into a into b will be 12q. This is what you should get when you square each of these numbers. But don't forget the goal. The goal was that the square of this positive integer, which is x squared that I'm looking for, should be either of these two forms. Either it should be 3m or 3m plus 1. But what I see right now is way more complicated than that. That means I need to do something more here to be able to see these numbers in the form that I want, 3m or 3m plus 1. So let's see how we can do that now. Well, the idea is really simple. You want to extract a multiple of 3. Either it should be straight away a multiple of 3 or just one more than that. When you look at 9q squared, it is definitely a multiple of 3. You can just write down the 3 outside like this. So this thing here, the 3q squared, is what is m for us. It just had to be any integer, right? So in my case, my m happens to be 3q squared. So here you'll just say for, because you have to tell what exactly this m is, for m equal to 3q squared. So we're done with this first one, and we saw, yes, it is one of these forms. Let me just number this. This is form number 1, this is form number 2. So we already got form number 1 here. Now let's see how I get the second one. This looks a little more complicated, but if you just look at it very carefully, just ignore the plus 1 for a while and look at these two here, 9q squared plus 6q. If you write a 3 outside, if you take 3 common from these, you will be able to write this as 3q squared plus 2q, and then keep the plus 1 that you had kept safe outside only. Yet again, here is your m, and so this entire thing becomes 3m, a multiple of 3 plus 1, which is form number 2 as we wanted. This time though, what is the value of m? M is 3q squared plus 2q. Let me write that here one second. Perfect. Now this third one here, again, I cannot obviously take 3 common from the whole thing. Why? Because I can take it from 9q squared, I can take it from 12q, but 4 is not a multiple of 3. That means this is not going to be form 1 for sure. So my job is to get it into form 2 because I have to prove this, no? I anyway know it has to be one of these forms. I don't have this option that this might not even happen. They're saying show that this happens. So it does happen. So your attempt, your focus should be to get this in the form a multiple of 3 plus 1. Now where do you get the 1? You will have to break this 4 into 2 parts. It will be 3 plus 1. So this 3 will be a multiple of 3, of course, and this 1 is what will stay outside. So just see how I take these three numbers, 9q squared, 3, and 12q, and I will take 3 common from them. So I write 3 outside. What I'll be left with is 3q squared plus 1 plus 4q. When you take it from the 12q, you'll be left with 4q, and plus this little 1 that we're left with. Which one is this? It is this small 1 that you're left with. Now you see, this entire thing will be the integer m that you're looking for. So this is also of the form 3m plus 1. And this time also you have to be very clear about what m exactly is. So m is equal to 3q squared plus 4q plus 1, whatever you have here on the inside. Yet again, you see that you reached form number 2. So that was the goal. You just had to show that no matter what positive integer in the world you take, if you square it, you're going to have one of these two forms. So we're successful in proving that. Here's form number 1, form number 2, and form number 2. We did not do anything specific. We didn't take any special numbers. It was just random x that we had taken, any positive integer in the world, and then we used 3 here as b, used the Euclid's lemma to first of all write the various possibilities for x itself. Then we squared it, and then we saw how we can write this square, these 3 squares, in the 2 forms that we are interested in, either 3m or 3m plus 1.